The first presentation in 2017 of the Computational Sustainability Virtual Seminar Series. The scheduled presentations through May are on the website at the center of your screen. I encourage you to go look to see what's coming up. This virtual seminar series is being organized by CompSusNet with support from the National Science Foundation and Cornell University. My name is Doug Fisher, and I'm the Director for Outreach, Education, Diversity, and Synthesis of CompSusNet. During the webinar, you can ask questions through the question and answer facility on Zoom, which will be related to the speaker as time allows. The speaker may answer questions right away. We'll perhaps prompt them or interject if it seems like that's best, or we'll wait till the end of the presentation. If you would like, find the chat window now and write hello to everyone. You can do that at any time, actually. It won't interrupt things. Today we're going to be having a presentation by Professor Zico Kolter. He's an assistant professor in the School of Computer Science and at Carnegie Mellon University. And he's affiliated with appointments in the Machine Learning Department, Robotics Institute, and Electrical and Computer Engineering as well. So Zico, I'm going to turn this over to you, and you can start whenever you want.
All right. Well, great, Doug. Thank you very much. Everyone, it's great to be here. Thank you all for attending virtually. I'm very excited to be talking about some of our very recent work, actually, to the point where some of it actually is not quite even in preprint form. We actually are posting the preprint on Monday for some of this stuff, but it's very, very recent. I'm very excited about kind of this direction in research, and so hopefully can get some feedback and some interest from everyone here. All right, so let me start sharing my screen now. Hopefully this all works. There we go. All right, it was giving me a spinning cursor for a second there. I was worried for a second. But I think all goes well. All right, does everyone see the main screen?
Yes. Okay,
perfect. So this talk is on, as I said, a very new sort of research idea that we're working on here, or at least new from our end. We're calling task-based end-to-end learning in stochastic optimization. This is joint work with my PhD students, Priya Donti and Brendan Amos. Priya, I know, is online, and Brendan might be sitting there also with her. I'm not quite sure. But hello. Correct me if I say anything incorrect in these slides, guys. You can just type in the text box, and Doug will alert me. But this talk's also going to be a little bit unusual in that I'm actually going to spend probably half the talk just trying to give the setting that we're addressing, because I think it's a setting that there's a lot of subtlety to, and so I want to kind of give a little bit of intuition about why we think this is an important problem, as well as what we think sort of is currently done in the intersection of machine learning and stochastic optimization, and then how we think certain things can be done better here. So let me start off with an example. And this example is a very common one. It's actually a very common use case for stochastic optimization. The example is energy scheduling. So the idea here is that I or you hypothetically are a system operator, and you want to schedule energy generation for the next 24 hours based upon something, but probably the thing you're going to base this upon most of all is some forecasted demand over this next 24 hours. And we're not going to really assume, we're not going to worry too much about the actual grid structure here. All this can be generalized to actually having a grid and power flow and constraints and everything like that. But I'm just going to have very simple constraints here. We're going to have some uncertain demand in the future. We'll talk about how we represent that later, but just think of it like some sort of Gaussian over uncertainty over my future demand here. And we also have things like generator constraints. So I'm going to have like a ramping constraint saying the generators can't turn on, can't change their power too much from one time to the next. And the goal is to find a generator schedule that minimizes expected cost while also, for example, respecting ramp constraints. Where the cost here I'm actually intentionally being a little bit vague about, but I'll define it more formally in a second. This is the things that we use as the example here. And you should think of the cost as something like, some sort of expected penalty you pay for undergeneration or overgeneration, right? Because this domain is stochastic, we always could have the potential for overgeneration or undergeneration in a very extreme case, but you kind of want to guard against the worst possibilities here. And that's where we're kind of using this stochastic optimization stochastic programming framework for. All right, so to be a little bit, oh, and I have to say this, so this figure here shows the past. It shows kind of the variables that we have as our in our setting here. We have things like the past demand. We also have other exogenous features like weather forecasts. We have some sort of things that we know, like the past demand. We are at the present, and then we have some future demand, which is uncertain, right? We're going to model this as a distribution. And so what this could look like, for example, is something like this. So this is again, a very cartoon thing. You probably wouldn't really schedule generation this way. But if you have, say, a ramp constraint on your generator, you may be forced to, over-generate a little bit in the nighttime here where there's the low demand coming up. And then because you don't want to ever have a situation where you get into, you cannot produce enough energy, you then want to make sure you're always sort of over the expected value by a little bit, maybe within some uncertainty range there. Right, so this is just a cartoon, it's a picture, but it's an example of something you might schedule based upon some cost function and some prediction or forecasts of your uncertain future demand. All right, so I'm going to define mathematical notation here a little bit. We will get into a little bit of math later on, so I want to just set variable names right now. So I am going to talk about all the things that we know, i.e. the past demand, but also things like weather forecasts that we have at the present time. I'm going to wrap all that in the variable x. Okay, so x always means things that we know. It means sort of the input features if you want to talk in machine learning terms. What we don't know, at least at the present time, is the y, right? The y is the future demand. And this is the unknown thing, at least at the present time. And so it's the thing that we have some uncertainty about, right? So we're going to come up with some model for what y actually may, with the values it may take on, in fact, given our current knowledge of x. And these two things, I should say, is just sort of standard machine learning notation, right? We have inputs and outputs to the system, and you compute some conditional distribution of y given your input. What we additionally have in a stochastic programming setting here is a decision variable z. So z's are the decisions we can make that actually let us take some action. For example, scheduling generation, really based upon our uncertain future demand. Okay, so that's sort of the three groups of variables we're going to talk about, and I will try to use those things consistently. But later on, I'll just say put the variables x, y, and z. I'll try to come back to this notion of past demand, future demand, and generation schedules. But just know those are my three classes of variables here. Right, so hopefully the setting is clear now that we sort of have past demand. We're going to use this to come up with a forecast for some uncertain prediction over the future, and then we're going to use that uncertain prediction to actually make some sort of decisions here. All right, so now I'm going to sort of formally frame my setting here, and in fact, I'm going to apologize. I see Warren down in the corner there, and I'm always very scared about talking too much about stochastic programming, stochastic optimization here, because I'm going to complete a lot of terms that he's going to be really annoyed about. So I apologize, Warren, to all these for all the mistakes I'm going to make here, or at least all the simplifications I'm going to make that completely obscure the interesting issues. But here's my notation, and so we can debate about whether this is good or bad later. So what I'm talking about from a formal sense, if you sort of know this stuff, is called really a single stage stochastic program. That's going to be my setting for stochastic optimization, which is by no means even the most interesting one. I mean, actually you can, by coming up with complex enough functions there, you can actually use this setting to emulate more complex ones. But of course, it sort of ignores a lot of the sophistication of actual the actual temporal modeling and stuff like that. So again, with apologies to Warren, I'm going to use this notation for my stochastic programming problems. Anyway, here's the stochastic programming problem that I care about. So remember that y is our sort of uncertain future, right? And mathematically what this means is that y is a random variable. So we're given a distribution over y, and our stochastic programming problem says, given this distribution, I want to find a generation schedule that minimizes some expected cost. And that expected cost, I'm going to always denote my objective, my sort of cost function I'm trying to minimize here as f, and I'm minimizing the expectation of f. And f is a function both of my random variables, the value that they actually take on, but of course then I'm minimizing my expectation of this function, and the decision variables I take on. And this is also subject to some potentially stochastic inequality constraints, which I'll call G, and then some equality constraints. And the equality constraints are usually not stochastic, at least not when it's written this way, because it's sort of hard to, it's very hard to find sort of arbitrary functions there that you can satisfy when they're a function of a random variable in the single stage setting. That isn't trivial, right? If it's random, it can often not hold with equality there, so it's sort of often written as not being an expectation when you have your equality constraints. And for convex programs, by the way, I should add that those equality constraints will always take on the form of some linear equalities. But again, what I mean here is we're minimizing some expected costs subject to some constraints, where the expectations, importantly, are with respect to my random variable y. So this is, again, I'm minimizing, I'm picking my z's to minimize some costs of my, say, generation schedule. The expected cost given the uncertainty I have over future demand. And so, for example, here's an example we can use, in fact, and we will use this example or something very close to it for our generation scheduling problem. The idea is we're going to minimize in this case, say, say that my planning task is that I'm starting at the first hour of the day. So I'm starting at hour 0. I have some forecast over my next 24 hours of what demand's going to be, or demand is the y variable. And my cost now is some function of the sum of overall hours of some factor, I'm calling it 10 here, times y minus zi plus, plus which is sort of our under generation penalty, right? So if our true demand y ends up being bigger than our generation, we pay a big penalty for not having enough generation on capacity. And the other thing happens if our zi is bigger than our yi, we pay an overgeneration penalty. So those are the two terms in that objective function there. They basically penalize asymmetrically the penalty we pay when we, in fact, overgenerate or undergenerate. Remember, in this cost function, y is actually the true, the actual future demand that we see later on. But then you take the expectation of this. That's where the random variable factors in here. And then it's subject to a constraint that the zi, and this is actually a non-stochastic constraint. It's just a fixed constraint here. Subject to a constraint that the zi's can't vary by more than some ramping constant over time. Okay, so this is a very, very simple problem. It's actually, this is sort of one of the simplest stochastic programming problems. It's called an inventory management problem. You have some, or similar to an inventory management problem, I should say, where you have some distribution over the future and you sort of pay a penalty if you overgenerate or undergenerate, or if you hold too much inventory or don't hold enough inventory. Usually in inventory management, you actually have to also buy them separately than that, but it's a similar cost function than those things. Okay, so hopefully that makes sense to everyone. It's sort of actually very hard to give these lectures when you can't gauge the audience and see if people have questions or not, but I'm going to have to go and, Doug, you'll interrupt me if there are chat questions on the asking kind of clarifying questions, right?
I will.
So I'll assume that everyone understands that perfectly and there's no confusion there at all. Okay, so, okay, so now the big question I would say is, how do we actually get our distribution over y, right? So I talked about how we have some distribution over y. This is our distribution over future uncertainty, distribution over future demand, which is an uncertain, sort of uncertain quantification of future electrical demand. But the problem is that to solve this stochastic programming problem, we really need a closed form, or at least the ability to sample from this distribution, right? So we can't just use kind of samples from the real world for this, because to solve this problem, you have to be able to essentially simulate different scenarios that may arise, or even have a closed form of approximation to your function. And the question, of course, then comes, how do we actually get this distribution over y? How do we know what this thing actually looks like? Well, we probably go about approximating it, right? Either with some simple statistical method or using a more complex machine learning model. But importantly, and this I know, fortunately, Warren and I agree on this point, despite what the stochastic programming community sometimes mistakenly thinks, this is not the real problem we care about, right? Solving this problem on the previous slide here is using some approximate distribution of the actual what's going to actually happen in the world. What we really care about is what happens when we actually run that policy, or that use that allocation in the real world, right? And that's not the same as what happens when we solve this problem, right? We're using an approximation to our uncertainty over the future. Okay, so hopefully that's clear. But how do we come up with this model, right? So first of all, this model we know over y, we know it's going to be approximate. But how do we come up with it? Well, the normal way of doing this is, and again, I'm going to come back to my notation here, where the past demand or other things we know is going to be called x, and the future sort of prediction we're making is going to be called y. And what we do is, the typical sort of strategy in machine learning is that you pick some parametric form of a model to represent your distribution of your future random variables, given your current things you know about, right? So basically you pick some parametric form, or non-parametric if you want, but you pick some sort of distributional form for our distribution, our conditional distribution really, of the future loads, given the current features, and we're gonna write this as P of y given x, and then semicolon theta, that means theta are the parameters of this model. So that's read as the probability of y given x parameterized by theta. And by far the most common thing you can do sort of in traditional statistics or machine learning is you just pick the parameters theta that maximize the log likelihood of observed data in the past. So essentially, what I do is very simple here. We collect a bunch of past days, right, where we know what the past was in those past days. We know the past demand, we know the weather forecast, etc. And for those days, I'm going to call that here yi. And then for those days, we also know what the true future, the real actual future demand was, which I'm going to call yi. And so I can come up with a model that will maximize the log likelihood of the probability of my data that I've seen, given my past inputs, my past features. I'm going to basically pick theta to make that probability as high as possible. And this is just classical maximum likelihood. I mean, people might even get mad at me calling this machine learning, though really machine learning is doing this as well. Or a lot of models do something very similar to this. So this is kind of how we typically build machine learning models. And this leads us to the following rather complicated process, I would argue. But this is fairly, I think, standard in a lot of kind of data-driven stochastic model learning slash. I'm getting a comment here saying my internet is unstable. Can everyone can still hear me okay? Okay. Very disconcerting comment saying that my internet is unstable. So we'll see how this.
You seem to be okay.
All right, perfect. All right, so the idea, I'm bad echo now, fortunately. I'll turn the volume down, but Doug, just kind of wave if you need me then, because I think that I'm gonna turn my volume down or I'm gonna have a very distracting echo. This is gonna throw me off. All right, so the whole sort of two-stage stochastic programming process, I would argue, goes something like this. The first step is that we want to learn our model, right? So we have a bunch of past data, and what we're going to do is we're going to learn our model, i.e., we're going to learn our parameters, theta, via maximum likelihood. I'm getting a bunch of comments here, so I'll assume there's all these people saying that they can hear me, and I'll assume Doug will jump in if otherwise. All right, so we're gonna use machine learning to learn a model of our future uncertain demand using maximum likelihood, and then now suppose that we're sort of given, and we're gonna sort of learn that model from data with maximum likelihood and kind of fix it, right? Maybe we'll update it with new data as it comes in. We're basically gonna think of that as a fixed parametric or non-parametric model that predicts or kind of gives us a distribution of uncertainty over our future given what we currently know. So that's, over our future y, given what we currently know x. So now the real sort of test of this system, of course, in stochastic programming is if we're given some new example, right? So I'm given some new example now, x prime and y prime. And these would correspond to, the actual x prime would be the actual features that I have today. So that's, the past weather as well as maybe weather forecasts, any sort of exogenous information I have, that would be the x prime for today. And y prime is the actual future demand tomorrow, right? So we don't know that when we can make our decisions, but there is some actual future demand that will occur. And so I'm going to denote that y prime. So when I say y prime here, I mean an actual fixed demand that occurs, whereas the variable y without the prime is going to refer to the distribution that we have over what we think the future is going to be from our machine learning model. So the process here is that in step A, we get our current features. We sort of figure out what's going on currently, and we form some distribution over what's going to happen in the future using our machine learning model. So that's step A. Again, we don't know what y prime is here. We don't know the future demand here at this point. We're just using our model to predict what we think the future is, or to model a distribution of what we think the future is. The next step is that we're going to use this model. Importantly, we're using the model here to solve our stochastic optimization problem, stochastic programming problem in this case, really. We're going to minimize over our decisions. Given this model's sort of forecasted uncertainty over y, we're going to minimize our expected costs subject to some constraints. And importantly, I'm going to call the resulting solution here Zstar of x prime. And I'm using this notation. These are an x prime parameterized by theta. And I'm using this notation here because even though it's not clear from the stochastic programming problem, Zstar, of course, here depends on both x prime and theta. It depends on x prime because it depends on the distribution of y, and in our machine learning, and theta. And it depends on both these two things because we're using our machine learning model to predict what y is going to be given x prime and parameterized by theta. So while Zstar here is just the solution of a stochastic programming problem, it really effectively depends on both our observed features as well as our model parameters theta. So this is probably actually the most, well, I'll get more complex in a second, but this is already getting fairly complex here. So I want to hopefully go slow enough that people can sort of get all this, but Doug, please do interrupt if there are any questions. Okay, so hopefully that's all clear. The idea is I observe my features, I use these to come up with a forecasted model for what's going to happen, and I use the forecasted model to come up with my, that's y, and I use my forecasted model to come up with my optimal allocation of what I should do, which I'm calling Zstar here. And I'm going to suffer, and then of course, what actually happens in the end is that I suffer a cost not based upon my model itself, but based upon what actually happens, the y prime that I actually see. So essentially, the example here is that I schedule my generation based upon sort of my prediction of what y is going to be, but the actual cost I suffer depends on what the actual demand really is in the future, and that's y prime. And importantly, this is the same objective function I'm assuming here, though it doesn't, you can actually generalize it pretty easily to other ones, but I'm going to assume it's the same objective function that we're minimizing in our stochastic programming problem. So we're trying to minimize this, but we of course don't know what the true y prime really is, and so we're going to use our sort of predictive model to guess what y prime could be in all its uncertainty, and then make our decision, and then suffer our costs based upon what f really is. So that's a fairly complicated process that we sort of went through there. But I would argue it's actually pretty common. And again, feel free, again, it's sort of always hard to talk about stochastic programming with Warren right there on my screen. But hopefully it's a fairly, at least at a high level, it's a reasonable description of this sort of single stage stochastic programming when you use a machine learning model as your way of generating distributions, which is already actually fairly complex when it comes down to it. It's using sort of two different domains that often don't talk to each other that much. So
Zico?
Already a fun thing. Sorry, Doug, you're asking a question right now.
Yeah, there's a question from James Boley.
Okay.
So solving step B would generally be closed form given the definition of F.
No, so solving step B, right? So solving step B takes the form of essentially solving a stochastic programming problem, for which there's all sorts of ways you can do it. We're going to think about reducing this to quadratic programs, just convex programs that aren't stochastic, and you can do that either by sometimes. You can do that either by what's called the sample average approximation, which essentially draw a bunch of samples and you solve it in a sample average case, you solve this program. Or you actually sometimes can get an expression for the expectations in closed form, but when it boils down to it, what you ultimately have is you have some numerical optimization problem to solve. But there's typically not a closed form solution. You have to solve something like a linear program or quadratic program, and oftentimes a very big one, in order to find this solution here. So that's a great question there. Thank you for clarifying.
He says thank you. Yep.
All right. Okay, so I would argue that there's something wrong here. And what I argue is wrong is that we're learning the model based upon maximizing log likelihood, right? That's our machine learning way of learning a model. But we're evaluating it using a task-based cost function. So our ultimate thing that we're trying to really optimize here is our cost that we get when we actually use this model to generate predictions or generate plans. Yet we're building this model not with that in mind, but just purely based upon kind of the likelihood of what may or may not happen. And this kind of makes sense because in some sense, maximum likelihood is the best thing you can do. But that's only really true if our true underlying distribution, that means i.e. the real world, is in our model class. So if the true world is in our model class, everything is great because maximum likelihood will find the true model parameters. We can find our actual model. So solving that stochastic programming problem actually is solving the real problem we care about. Unfortunately, that's not really ever the case in machine learning. So we never actually have the case that the true world is in our model class. Instead, the model that we're learning is always an approximation. Sometimes a very bad approximation to the real world. And in this case, these two objectives, getting good log likelihood and minimizing some minimizing some task-based cost function, actually are competing objectives. They're aligned, of course. They're similar, of course, but they aren't actually the same thing. They can be subtle differences here in sort of what regions of the space are important to model and what aren't. And this is typically ignored when you do this sort of two-stage process of first learn a model, then run stochastic optimization. All right, so what do we want to do is, in theory, a pretty simple idea. It's appeared in literature before, so it's gone by a lot of names in the past. One of the better examples I've seen of it is some work by Yoshua Bengio in 1998, where he was looking, so this is almost 20 years ago now, where he was looking at doing sort of machine learning for financial predictions. But the idea is very simple. We're going to adjust the model parameters, that is the parameters of our representation model, to minimize the actual, the actual performance of the system, sorry, the actual costs of the system, I should say. Maximizing performance, I guess, depending on how you define performance. But anyway, we are adjusting the model parameters to actually minimize the cost of the system as it behaves in the real world. So in other words, we're going, and I'll write this down at the bottom here, but basically we call this task-based end-to-end learning. And what this is essentially a framework for adjusting the model parameters in stochastic programming, or stochastic optimization more generally, to optimize, not to optimize the log likelihood of our model, but to optimize the closed loop performance of the resulting system. So when I use that model to make my decisions in a stochastic programming setting, how well do they actually work? And that's what we're going to actually try to optimize. So formally, and I'm going to just omit the constraints here just for simplicity, but what we want to do is we want to minimize over theta the sum, and again, the superscripts I in this optimization problem here correspond to sort of real instantiations we've seen. So we have a big data set, and we're going to try to find model parameters such that when I use this model, again, in a stochastic programming setting to generate my plan, that's what I call Zstar here, and then I evaluate it as how well it did on the real system, I do as well as possible. Okay, so that's our task-based end-to-end learning framework. I saw a bunch of questions there, Doug, so maybe people, is there anything relevant I should jump in and answer, or are they all just, sounds good?
They're all just system updates.
Okay, perfect. Okay, so hopefully that makes sense to everyone, what I'm doing here. So I want to do something that seems kind of strange, right? I'm going to adjust my model. This is the model I'm using for stochastic programming. But I'm going to adjust it in a way that's kind of agnostic to whether or not the model is accurate in making predictions, right? All I care about is that when I run essentially my policy with this model, right? When I make decisions based upon this model, those decisions end up performing well on actual data that I've seen. And this is, and I said this is not sort of a, we're not the first ones to have this idea, but I think in this general setting of sort of changing models for stochastic programming, I think it's a very sort of powerful paradigm, and we come up with sort of a very nice way of doing this. So how do we actually then solve this problem? How do we solve, because that optimization problem, it looks actually fairly easy in some sense, but it's actually kind of a subtlety here that makes it kind of tricky. Let me, I lost my cursor there. Okay, so in theory, we're solving a machine learning problem like any other here, right? We just get a sum of loss functions that we want to optimize. But there's a little bit of a subtlety here that makes this a little bit tricky. The problem here is that if we take gradients of this cost function, something kind of unfortunate happens here. So I'm writing here actually in sort of the Jacobian form, the multivariate calculus form. What happens when we try to take the Jacobian of my loss function here, my f function, that's what I'm trying to minimize, with respect to my parameters theta. This is, by the way, how you form gradients for machine learning, and then you take a step in those gradient directions to optimize your parameters theta. But if you do this and just expand this out with the chain rule, something kind of very unfortunate happens here. And what unfortunately happens is that you have a term that looks like that one that I have the arrow pointing to. So this term is the partial derivative of Zstar with respect to our model parameters theta. And remember, Zstar is the result, the argmin of our optimization problem, of our stochastic programming optimization problem. So how do you actually go about differentiating the solution to an optimization problem with respect to the parameters of the model that were governing that problem? And so this is actually something that there's been some recent work on, and very recently also, this actually just came online yesterday. We published this yesterday. There has been a lot of work in kind of doing similar things like this, like differentiating through optimization problems, for example, by unrolling optimization procedures. But actually, but for the specific case of quadratic programs, and actually even more so than that, the specific case of quadratic programs, they're sort of governed by a very particular form of backpropagation, or rather where we want gradients in a very particular form of backpropagation. We presented a method for analytically computing the derivative of the solution to an optimization problem with respect to the parameters of that optimization problem. And importantly, this is done without doing things like unrolling the actual optimization procedure. That kind of stuff has been done a lot in the past. As far as we know, this is sort of the first time we've seen general constrained optimization in the QP form differentiated through, not in terms of differentiating the objective. That actually is very common, to differentiate the objective functions with respect to the parameters, but to differentiate the actual solution, the output you get from that with respect to the parameters. We haven't seen that, at least not used very much, even if the math is actually well understood there. And so we actually have some recent preprint on this, as well as some code we released on this sort of methodology of how we go about doing this. And in particular, let me just take a brief detour here to sort of what this actually means. But we do it in this paper, we do it in particular for the case of quadratic programming problems. So a quadratic program is a program where we have a quadratic objective, so you're trying to minimize Z transpose some matrix positive matrix Q, Z plus P transpose Z, subject to some linear equality and inequality constraints. And what we show how to do is that we show how to compute the necessary Jacobians of the system with respect to the argmin of that optimization problem. And in particular, actually, we don't compute the Jacobians themselves. And then this is getting, I won't cover this in any detail because this is sort of just specifics here. But we actually don't compute the Jacobians themselves. What we actually do is show how to efficiently compute backprop through these Jacobians. So the backpropagation algorithm is actually what we end up doing with sort of the work, and that actually doing this efficiently for QPs on a large scale is actually not something we've seen before. And so what we developed is an efficient solver for this and an efficient backpropagation kind of way of computing backprop these layers. And that's what enables us to be practical on a very large scale here. And for those who are curious, I mean, the paper I had in the previous slide But the derivation here, which again I think is sort of probably likely very known mathematically, but which I think is interesting from a practical standpoint, involves matrix differentials of the optimality conditions of the solution to that problem. Okay, so that's all I'm going to say about sort of how we do this. Basically, it lets you take, if we move back a few slides now, these things we develop let you solve this thing, at least for the case, this sort of Jacobian here, at least for the case of quadratic programs. And then in this current work, we extend it to the case of general stochastic programs, stochastic convex programs, where we essentially use a sequential quadratic programming technique to iteratively solve this method. And then at the solution, you have a similar way of getting all the Jacobians that you need, or at least a way of back propagating through the Jacobians. And as I said, sort of unusual. We were hoping to get it out by today, but I think actually we're just trying to finish some things up. So we're going to put the preprint out on Monday. Please contact me if you would like an advanced copy, or I guess not advanced because it's going to be out very soon. But if you like a pointer when that comes out, let me know, and I'm happy to send over email. Okay, so let's see now how this actually works. So what I'm going to do now, and I'm going to go back to the exact example that I had before. Very minor changes actually, but it's essentially the exact same example I had before. And I'm going to apply this technique to scheduling generation for a power plant, or hypothetical power plant at least, based upon Pittsburgh electrical demand data. So what we're going to do is we have in our data, we have 4 years of data from of electrical demand from the Pittsburgh area. We also have the weather forecast and the weather that happened during this time. And so using this, what we're going to do is we're going to model the future demand. So given our current information like weather, past demand, etc., we're going to model the future demand as a distribution, a Gaussian distribution, with some mean that depends on our parameters. And actually that mean mu as feature of x is actually a neural network. So we're using a neural network to predict the mean of our Gaussian distribution, plus actually a fixed covariance to that distribution. So this is going to be our representation of uncertainty of our distribution. And in fact, the parameters theta here correspond to sigma, which is our covariance, and the neural network parameters specify our prediction of the mean. So that's sort of jointly what our parameters theta are. I should say we tried a little bit to come up with a heteroscedastic model, i.e. theta, try to come up with a model that has sigma depend on x2, but it didn't seem to add any predictive capabilities here. So at least for this domain, it didn't seem too important. So we just have a fixed covariance for all points that we have, of course, a feature-dependent mean prediction. And then the stochastic optimization problem we solved is, sorry, and I should clarify, when I say has closed form expression here, I mean the objective has closed form expression. It ends up being a quadratic program, but the quadratic program is we minimize the expectation of some constant times our overgeneration times some other constant times our undergeneration, that's the second term there, plus an additional quadratic term too. That last term is to make it a QP. It's actually for sort of smoothness reasons, and we usually pick other terms to be kind of bigger than that, so that last term is not too important. But we minimize all that, and when I say, and actually there's no closed form expression for the solution to this problem, but there is a closed form expression actually to that expectation when you have a Gaussian distribution. So this is sort of a fairly simple distribution, and you can actually come up with a closed form expression for what that expectation is. It involves essentially the Gaussian CDF and the Gaussian PDF. Subject to then, of course, some additional constraints like on ramping, and those constraints, when you add those to the objective, there's no longer any closed form solution. And so what we do is we then solve this problem using our differentiable optimizer, essentially, where we can where we use a sequential quadratic programming technique to solve this problem, and then we can back propagate the performance of this sort of resulting solution to actually change the model itself. So we're going to use this optimization problem here as our policy, and we're going to then change the model parameters in order to improve the performance that we see on the real world. That's basically this function here is what we're optimizing. So Zstar here is the solution to that optimization problem, and then we adjust the model parameters to minimize the expected sum of these costs as they occurred on real data. So now I just want to show you very, very briefly kind of how this, what this looks like in terms of the results that we actually see for things like this. So here is one example of these two models. So the important lines to sort of note here are going to be the green line and the red line. Those are both performance of the system on new examples. So we have a training set and a test set. These are all sort of examples. Those two lines show our test set performance, which of course would actually matter. It doesn't really matter how well we do on days we've already seen before, or how well we would do in hindsight on days that we know where we know the answer. But what we've done here is we've trained two models. So the red model you'll see here is a model trained just to maximize the log likelihood of our prediction error, essentially, which for a Gaussian distribution corresponds to mean squared error. We're minimizing the sum of mean squared errors of our predictions, essentially, as they kind of roll forward in the future. And I should say mean squared error plus errors plus covariance estimates, right? So it's actually a Gaussian likelihood that we're minimizing when we have this thing, but for a Gaussian, root mean squared error is a pretty good proxy for what it's minimizing. The green line is the model that we get when we, instead of trying to optimize prediction error or log likelihood of the data, we instead actually adjust the model parameters just so that they give good performance on sort of as kind of black box policy parameters. In other words, we adjust them just so they give good performance on a resulting task, at least as in terms of data we've seen in the past before. So again, we're kind of using another way of putting this is we're using the model parameters as sort of just policy parameters that we can adjust, and we're just adjusting our policy parameters in a way that actually minimizes the cost that we observe in the real system. So this was what's showing what happens with, though, our prediction error. So and this is interesting, right? Because it's sort of as expected, but it's still interesting. As you would expect, if you evaluate the sort of performance of the system with respect to the actual root mean squared error of the predictions, in other words, how good is the model doing in some sense, our sort of specially optimized model here does worse, right? So we are actually getting worse predictions as measured by root mean squared error than we were if we just optimized the task, the root mean squared error loss, or the Gaussian likelihood. But if you look at the actual cost you suffer, that is the exact opposite here. So it turns out, if you actually look at the cost you pay in terms of your task loss, that's the actual sum of these FI terms as evaluated on new data points that we haven't yet seen. Our task-optimized, our task-based end-to-end model works quite a bit better. It improves by about 17 or 18% over the performance, over the cost you suffer when you just try to optimize the model. And again, these models actually have fairly low error here, right? So going back, we're talking about, for 1 second, we're talking about root mean squared errors in the 0.07 range at the high end, and this is measured in units, I should say, of gigawatts. And the number of gigawatts that Pittsburgh consumes each day is in the 1.0 to basically 2.5 kind of range, maybe a little bit more or less. That's sort of the overall range. So these are pretty accurate predictions, actually. I mean, as we all know, it's actually not that hard to forecast electricity demand. It's one of the easier things to forecast. So these are pretty easy models, or relatively easy prediction tasks. Yet despite this, we still get a very big benefit by actually optimizing the loss that we care about, namely the performance of the system when we use this model to make predictions. And I think this is a really nice paradigm because it lets us think about what is the thing that we really care about. Do we really care about root mean squared error when we make predictions? Well, sometimes, but oftentimes we actually care about how well that model will serve us in doing anything future with this model, and how well it will serve us in making decisions going forward. And so I think this paradigm of optimizing task loss is actually a very powerful one, and this notion of differentiating through the solution to optimization problems is actually a very nice way to accomplish this. So that's actually the entirety of the talk I have. Sort of in summary, in stochastic optimization, it's more traditional, I would say, to learn a model that just sort of tries to model the underlying stochastics from a maximum likelihood setting. But I would actually argue you don't want to do that. necessarily, or maybe you want to start there, but then you want to fine tune your model with something else, right? You actually want to learn a model that leads to the best closed loop performance of the system when you actually run that model on a domain that you care about. And this is actually, though we presented it in a sort of fairly simple example here, this is actually a very general framework for when we have an optimization-based task. How can we actually differentiate through that task to adjust model parameters in order to optimize the performance of that policy on a real system? So as I said, a preprint on this is going to be available on Monday. I was hoping to have it up today, but unfortunately it needs a few. We want to make a few last-minute edits. Please do email me though if you'd like a pointer or anything like that when we do in fact post it on archive. So thank you very much. It was great to give this virtual talk. I think it actually, despite the travel, it seems to work out pretty well. So thank you very much. And are there any questions? Warren's a question. I never would have guessed he has a question. All right, Warren.
Okay, so mine's very basic, Zico.
Yeah.
So I just want to understand the problem. So this is an energy storage problem, a unit commitment problem. What's the actual physical problem? Okay,
so this is just a allocation problem with ramp constraints. So the only problem is I want to. I mean, you can think of it like unit commitment, but it's sort of like hour ahead non-unit, day ahead non-unit commitment. It is somewhat of an example problem. I mean, this is not the actual grid planning task people do. This is
unit commitment without energy variable. So aggregate. It's like an aggregate energy planning problem, but it's still a problem where the decisions have to be made. Let's call it the day before.
Yes.
All of that at time zero.
Correct.
So at time zero.
At time zero. Yes.
At time zero, you specify a schedule for all 24 hours.
Correct.
And the Z variables are all locked in. They're all F0 measurable.
Right.
Okay.
So the context here is that we pay some cost in the future, which is not, I mean, the idea would be there would be recourse afterwards, but we are essentially, so it's sort of the day ahead problem, and that we are planning it in a way that where we suffer a big cost for undergeneration and a small cost for overgeneration, basically commensurate with the ultimate cost you pay for the hour ahead or the real time scheduling when you would do that.
The term that the stochastic programmers use is they call this simple recourse.
Sure. Yes.
That's their buzz phrase for this.
Perfect. So yes. And the simple recourse, I guess, was just captured by the cost, right? It's just captured by the inventory cost that you have.
Mm-hmm.
Yeah.
Zico, I have, I guess, a general question, or putting it in a more general setting. So in the end, I guess what you are highlighting is the result of how we try to, approach problems. Because typically what we do, there's a department doing the optimization, there's a department doing prediction, so we separate them.
Right.
But in the end, what you are saying is, no, I mean, basically our end goal is this problem, so we should
it's not like
a single path. So you are folding literally the prediction problem, the rise into your overall problem, correct?
Right. So we do our predictions in some sense,
which is why
we learn our predictive model at least with the final task in mind. And I think that's a sort of a very important thing to think about as prediction and decision making become more intertwined, which they already are, but this is going to keep happening more and more. That we just keep thinking of these two things together rather than as separate tasks. That's a great way of.
Yeah, but I guess in the end, it's like a trade-off in terms of complexity, because I mean, it's like the airlines. The airlines could predict design a schedule considering everything at the same time. But then you would have such a complex model that in order to use this model, I'm not sure how you could scale it up.
Yeah.
So my question is along those lines. I mean, the trade-offs.
Yeah. So that's a great question. So the trade-offs, I think it's less about model complexity in some sense. You might consider it about, the complexity of the training process, whether that's, how easy it is for someone to pick this up or not. But the model form is the same in some sense, right? Because the model form is, the model parameterization we're using here is actually the same model parameterization. It's just that we're optimizing a different objective, either a task-based objective or a likelihood-based objective.
Mm-hmm.
I would say one thing sort of crucially though, in terms of the trade-offs involved. So when you do this process, the advantage is that you are specifying, you're specializing your model for a specific task. The disadvantage is that you're specializing your model for a specific task, right? If you try to use your model now for a different task, it could be completely wrong because there's no even notion of a predictive accuracy here. It's really just about the performance of the resulting closed loop system. So you could actually perform quite poorly when it comes to a new task that you haven't seen before. So I think that's really where it sort of the big trade-off occurs. If you're using the same model to solve a lot of different tasks, then it's going to be very difficult to use this approach because you have one model and are you really going to adapt it to each different task? I'm not quite sure. Whereas if you have one task you really care about, then this kind of thing makes sense because it does give you a sort of a way
to
think about how to do that.
Yeah, I mean, I really liked this your talk. It's really exciting, and I see your point. I mean, I fully understand this issue that indeed, we don't really, the end result is this minimization, so I really don't want to have an intermediate step where I go, but go and do the, try to predict the Y's.
Right.
But I guess at the same time, it is a bit also, what about interpretability?
Yeah. But actually, I want to highlight that
let
point.
me just, but this is interesting because I guess, this is like, cars, we have self-driving cars out there, and, the car doesn't even know what a car means.
Right, yeah. No, that's a great point. So actually, let me drill down on this a little bit. So I would actually argue that what we're doing is kind of actually an intermediary between a fully black box approach and kind of a fully model-based approach. So we could always go the route of actually, and we have the comparisons in the preprint available actually on this thing as well, though I didn't highlight them here. We could also go the route of just having sort of a complete black box policy, which prescribes our output just as a complete black box function of our inputs, right? So we actually find the optimal allocation just as a black box function of the inputs that we know about right now, right? So we could do that too. What this is actually doing, what this model is actually doing, this model is actually using the same form of the model in some sense as the intermediary. So it's using the form that we know or that we believe a model has in order to make its predictions. And then we tweak the parameters of that model a little bit to be more task specific. So we actually are still using a model, which, again, if we look back, they aren't awful predictions, right? It's not like we're foregoing all predictions. We still have some prediction here. It's just that we sacrifice a bit of accuracy in our predictive, in our sort of predictive sense, in order to achieve more accuracy in our task-based sense. Yeah. So I think it's actually, and then personally, I sort of also sort of believe philosophically that we do want to have a form of model here. We don't want to go the route of just having a complete black box policy that we can't understand at all. But we want to specialize that model for a specific task. And so I think this strikes kind of a nice balance between those two extremes.
Yeah. Now, very interesting. Yeah, I do see that indeed, that nuance that you keep a model. Right. It is actually quite interesting.
Yeah, exactly.
Oh, very exciting. Very good.
So we have a couple of questions.
Ooh, I'm getting a feedback there.
Yeah, nice feedback.
It's interesting.
So,
all right, let me. Okay, I can read them. Let's see.
We have one from Jane.
But I think when you speak, it causes a little feedback on my end.
Yeah.
So maybe what I'll do is that I'll stop my screen sharing now and switch to video so everyone can see me again. And then I can read the questions. Okay, so Kim Baraka asks, as a future work direction, do you think it will be possible to learn to tune the model class itself from the task performance data observed? So I guess the question here is, can you expand the model class? So actually expand the class of allowable models, not just tune the parameters within a specific model class. Is that, Kim, is that correct? Okay, so hopefully that's, yeah, I think she said that was correct. Yes, so in some sense, I mean, again, I'm gonna sort of maybe give an unsatisfying answer here because it's the sort of machine learning person in me thinks of all model classes as just sort of larger sets of parameters you can explore, right? So in some sense, every model class is just a slightly wider set of model parameters you could have. So I can just use a more complex class of models, right? And in fact, for this function, we were using a neural network, so for the function class, so for the model class. So it's a very, you know, the representation capacity of this model is very, very high. And so it's not clear to me that we need to differentiate between learning model classes and learning parameterizations of a model within some very large and expressive class. But I think that we can certainly, I mean, because the model class, if you evaluate it on a test set on your task-based objective, is perfectly fine to select amongst. You can certainly do hyperparameter selection or things like this based upon another validation set in the same exact way. So it's definitely possible to learn model classes, yes. But I would say we really do have the ability to kind of use these sort of very, very high capacity models in the first place, like neural networks, and that kind of makes it our choices there a little bit easier. Okay. Oh, I see. So Kim clarifies, says the idea would be learn the optimal model class and then switch back to the semantic complexity for decision making. I guess you could. I'm sort of, again, I'm actually suspicious. So again, this example here that I have. Oh, sorry, I'm showing. I'm not actually on. The example I had at the end there, that was a fairly complex neural network class, right? So I don't know how I would take that and sort of extrapolate from that what the optimal sort of subclass within that class of neural networks was, and then fit with maximum likelihood. I mean, that was one fit with maximum likelihood and one fit with this task-based loss. It's very sort of unclear to me how you would go about doing that. So I don't think it's impossible, but I'm not quite sure the best way of going about it. I wouldn't use it to fix a model class. I personally wouldn't use it to fix a model class and redo maximum likelihood estimation. But you can fix some parameters with one and then learn other parameters. You can sort of do all these things that you want to do. Okay, so then James asks, is the tricky part differentiating the optimization task or linking it to the model to continue backprop? I think there's actually sort of both challenging tasks. So really the other paper we had that I pointed out was really about the differentiating the optimization part. This one was much more about when our optimization problem is the form of a stochastic problem where we have sort of our parameters that we care about are the things that govern the stochastic model. How do we differentiate through that process to adjust model parameters? So I think they're both kind of tricky in some sense. They're both things that I hadn't seen sort of people doing in that same context before. But they're both necessary components here that do make it kind of challenging to do this. We do though actually, and with and part of actually the reason for the going till Monday is that we are releasing code with all these things. We have code for our other paper out, including a integration to a fairly nice framework, which lets you actually run this on your run a fairly fast GPU-based QP solver that we developed, and also differentiates through them. And then we're going to have code for this too. So hopefully, some of the challenge there, the trickiness will be made easier by the availability of libraries to do a lot of this stuff. Okay.
I think that's it.
That's it? No more questions. Okay. Amazing. I guess we are over time, so we can end here.
James, thanks you.
All right. Well, thank you to everyone for listening, participating virtually.
Good answer. But we are past our hour. I want the great.
I'm mute. Okay.
I can't hear many people. I think a lot of people are on mute here, but well, if everyone can, I think people can hear me still, so I'll sign off now. Thanks everyone for coming. And please email me if you have any follow-up questions. You want to learn more. I would love to chat about this more. As I said, it's sort of very, very much ongoing stuff. So I would love to figure out how to do it better, or maybe in different applications. So thank you.
Okay, great. Thanks.